I am Prashant Vishwanath Dhanshetti, Assistant Professor, Department of Civil Engineering from Walchand Institute of Technology, Solapur. Today I am here to explain you about the slope and deflection of a cantilever beam with uniformly distributed load using conjugate beam method. The learning outcome of today's lecture is that the students will be able to construct the conjugate beam for the cantilever beam. They will be able to calculate slope and deflection of a cantilever beam with uniformly distributed load. Now, what is a conjugate beam? A conjugate beam method is the method used to determine the slope and deflection of the beam, in which the imaginary conjugate beam is constructed from the real beam and the shear forces and the bending moment of the conjugate beams are equal to the slope and deflection in the real beam. Now, what is the real beam? A beam with actual loads and support conditions is known as real beam. And what is conjugate beam? It is an imaginary beam of length equal to that of original beam, but for which the loading diagram is M upon EI diagram. Now, to draw the conjugate beam, it is necessary to know the conversion of the support from real beam to conjugate beam. So, for simply support or roller support in actual beam, in conjugate beam they will be treated as simply supported beam. The free end in the actual beam will be fixed end in the conjugate beam, and fixed end in the real beam will be free end in the conjugate beam. Then slope at any section will be equal to the shear force at the corresponding section of the conjugate beam. Deflection at any section will be equal to bending moment at the corresponding section in the conjugate beam. For a given system of loading, the loading diagram for conjugate beam will be M upon EI diagram. Bending moment diagram, if it is positive, that is sagging in actual beam, it will be M upon EI diagram, which is acting downward. For negative bending moment, that is hogging, the M upon EI diagram will be acting upward. Now, here there are the steps to draw the conjugate beam from the real beam. First, draw the bending moment diagram for the real beam, then divide the magnitudes of the bending moment by flexural of rigidity, that is EI, and draw M upon EI diagram. Draw the conjugate beam having the same length as that of real beam and plot the loading M upon EI diagram, then apply the support as described in the previous slide. Deflection for a given real beam will be dash for the conjugate beam. Here pause the video and try to write answer on a paper. The deflection for a given real beam will be bending moment of the conjugate beam. Now, you will find the slope and deflection of a cantilever beam carrying uniformly distributed load over the entire length by the conjugate beam method. So, let L be the length of the beam and it is carrying a uniformly distributed load, that is W per unit length. It is fixed at A and free at B. So, now first of all we have to find out the bending moment. So, if we see the deflected shape of this beam, so this will be like this. So, this YB will be the deflection at B, and if we draw a tangent to this deflected shape and the angle making of this tangent with the horizontal will be the slope, that is theta at B. So, to draw the bending moment, we will consider the right portion only. So, bending moment at free end is 0. So, bending moment at A is equals to load into distance. Now, load, this will be uniformly distributed load. So, it is W into L, that is the total load, and the distance, that is it is acting at this CG point, that is L by 2. So, multiply by L by 2. So, it is WL square by 2. The bending moment diagram and M upon EI diagram is as shown in this figure. So, this is the bending moment, and if divide this bending moment by EI, that is flexural of rigidity, So I will get M upon EI diagram. Now to construct a conjugate beam, the free end is converted to fixed and fixed end is converted to free. So now the end B will be fixed and A will be free. So this negative loading M upon EI diagram is upward for hogging. So this is the conjugate beam. Now let theta B be the slope at this B point and YB be the deflection at B for this given cantilever. So theta B will be equal to shear force at this B star for a conjugate beam. So theta B will be equals to, this is the shear force means the load of this portion. So the area of this loading diagram will be 1/3 base into height. So 1/3 base is L total into height is WL square upon 2 EI. So it will be equals to WL cube upon 6 EI radians. So theta B is equals to WL cube divided by 6 EI radians. Now YB is the bending moment at B star for the conjugate beam. So here if I calculate the bending moment at B star, so that will be equal to deflection of a free end in real beam. So bending moment will be equal to this load into CG of this from B. So that YB is equals to load A star, B star, D star, this into distance of CG of this A star, B star, D star from B. So this load will be 1/3 base into height, 1/3 base is L into height is WL square upon 2 EI, and the CG will be 3/4 of L from end B. So solving this we will get YB is equals to WL raised to 4 divided by 8 EI. Now we will consider a second problem, that a cantilever beam is carrying a uniformly distributed load up to a length A from the fixed end by conjugate beam method. Now first we will find the bending moment at C, B and A. So bending moment at C is 0 as it is a free end. So bending moment at B will be also 0 considering the right portion only as there is no load. So the bending moment will be 0. Now the bending moment at A will be equals to load into distance. So the load will be this W per unit length into this distance, that is A, multiplied by this CG from A. So that is W into A by 2, that is WA square by 2. So the bending moment diagram and M upon EI diagram is as shown in figure. So this is the bending moment diagram, and if I divide it by EI it will be M upon EI diagram. So now we will construct the conjugate beam. The free end will become fixed end and fixed end will become free end, and this is the parabolic curve. Here the unit will be WA square upon 2 EI. Now let theta B be the slope at B and dy by dx at B for a given beam. YB be the deflection at this point. So then the slope according to conjugate beam method, that is theta B, will be equals to shear force at B star for the conjugate beam. So if I take a shear force at this part, so that will be equal to slope at point B in the real beam. So now shear force means it will be the load acting on this A star, B star. So theta B is equals to 1/3 base into height. So 1/3 base is A, height is WA square upon 2 EI. So that will be equal to WA cube upon 6 EI radians. So theta B will be WA cube upon 6 EI radians. So let YB be the deflection at point B, which is equals to bending moment of the conjugate beam at B. So bending moment at B star is equals to, that is load of A star, C star, D star into distance of CG of A star, C star, D star from B portion. So the load will be 1/3 base into height and the CG of this will be 3/4 of A from B. So load into distance, that is 1/3 base is A into height is WA square upon 2EI into CG will be 3/4 of A. So solving this we will get YB is equals to WA4 upon 8EI. Let theta C here be the slope at C. So see, when this beam will bend in a curvature, so it will be curve up to point B, then it will be a straight line as there is no load in BC portion. So theta C is equals to shear force at C star for the conjugate beam. So shear force at this point. So the load at this will be equal to shear force at C. So theta C is equals to 1/3 base into height. So 1/3 base is A, height is WA square upon 2EI, that is equals to WA cube upon 6EI radians. YC is equals to bending moment at C star for the conjugate beam. So that is load into the CG of this load from point C. So YC is equals to 1/3 base into height, and the CG will be 3/4 of A plus L minus A, this distance. So YC is equals to WA cube upon 6EI into bracket, that is 3/4 of A plus L minus A. So multiplying this WA cube upon 6EI to this first 3/4 of A, and again multiplying this WA cube upon 6EI into L minus A. So we will get YC is equals to WA raised to 4 upon 8EI plus WA cube upon 6EI into bracket L minus A. This is the deflection at C in the real beam. So these are the references which I have referred. Thank you very much for watching my video.